If you're guessing when to call a bigger model, you're wasting money or shipping errors. Let's turn noisy signals into calibrated thresholds so escalation is automatic and defensible. You get a stream of model answers. Some are great, some are confidently wrong. You want to call the expensive expert only when it matters. By the end of this video, you will know how to turn raw scores into usable confidences, measure how honest those confidences are, and pick an escalation threshold that balances cost and correctness. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Calibration for LLM confidence is about trust. In practice, the problem is this. Your base model returns answers and a score. That score seems like a probability, but it's not guaranteed. Teams often call a stronger model whenever the score is low, or randomly, and that wastes credits. Success is when low confidence cases go to the strong model and high confidence cases stay put, with predictable costs and error rates. The downside is you trade extra latency and compute for safety. Compared with always calling the strong model, this pipeline can cut cost by a large factor at small risk. At its heart, calibration asks a simple question. When the model says it is 70% sure, is it actually right about 70% of the time? If not, you can rescale and fix that. A tiny example is helpful. Imagine 5 answers with raw scores like -1, 0, 1, 2, and 3. Those are logits, raw model numbers. Apply a sigmoid to each and you get probabilities like 30%, 50%, and so on. If the model is overconfident, those numbers need softening. If they are underconfident, you may be wasting escalations. We will build a small pipeline that takes logits, turns them into confidences, measures calibration, decides escalation by a threshold, applies temperature scaling, and then chooses the cost-minimizing threshold. This snippet converts toy model logits into confidences and checks accuracy. We define logits as raw model scores and Y as ground truth correctness flags. The list P applies a sigmoid to map each score into a probability-like confidence. We compute ACC by thresholding each confidence at 0.5 and comparing with the labels. Finally, MC captures the average confidence to gauge overall certainty. The printed pair shows how accurate the model is and how confident it feels on average. Next, we need a metric that penalizes confident mistakes, not just wrong answers. This snippet measures calibration quality using the Brier score. It compares each confidence in P with the true label Y and averages the squared differences. The function computes a single number where lower is better, combining sharpness and calibration. Unlike accuracy, this metric penalizes being confidently wrong more than being unsure. The printed Brier score summarizes how trustworthy the confidence values are. Now let's use those confidences to decide who gets escalated to the stronger model. This snippet chooses which cases to escalate based on a confidence threshold. We first compute pred from P to simulate base model decisions. The variable tau is the escalation cutoff. Items below tau go to a stronger model, trapped by IDs. We count baseline errors as error 0, then recompute remaining errors error 1, assuming escalated items get fixed by the stronger model. Increasing tau escalates more requests, reducing errors but increasing cost. Decreasing tau does the opposite. The printed counts show how escalation changes errors. Calibration often changes where the threshold sits, so let's calibrate next. This snippet calibrates confidences with temperature scaling before escalation. The parameter T rescales logits, producing calibrated confidences PC that are usually less overconfident. We then reapply the same tau to PC to decide IDS2 for escalation. The remaining error, error 2, mirrors the earlier logic. assuming escalated cases are corrected by the stronger model. Increasing T softens confidences and typically escalates more requests. Decreasing T makes the model bolder and escalates fewer. The printed result shows how calibration changes escalation volume. Finally, we want a principled way to pick that threshold based on money and mistakes. This snippet finds the threshold that minimizes total expected cost. We define TOWs to test, CE as the penalty for a wrong answer, and CS as the cost to escalate. For each T, we add error cost for non-escalated mistakes and escalation cost for low-confidence cases, using calibrated confidences PC and base predictions PRED. The list costs holds total cost, TOW, pairs, and best picks the minimum. Larger CE pushes toward higher TOW and more escalations. Larger CS pushes toward lower TOW. The printed choice is the cheapest escalation policy. Recap: calibration converts raw scores into honest probabilities. Use the Brier score to measure trustworthiness. Then pick a threshold by weighing escalation cost against mistake cost. One practical next step is to tune temperature and the escalation cost in the same run. Try a grid of temperatures and escalation costs on a held-out set, and plot total cost versus rate of escalation to find robust settings. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.